Hello everyone, my name is Nathan Noble. Today I'll be presenting my project on emotion detection for Math 437. Let's get into an introduction. Start off with a quick introduction. Alright, so let's quickly go over the importance of the problem. So emotion detection is simply the process of identifying and understanding a person's emotional state, often done by analyzing facial expressions or body language. It can be useful in many different avenues. For example, monitoring mental health during video therapy or medical consultations, improving business insights via real-time sentiment analysis, and most notably, potentially enhance human-AI interaction by enabling empathic AI responses. So what is my motivation for this project? So the biggest thing is I want to gain experience using convolutional neural networks, otherwise known as CNNs. Another motivating factor was to build something interactive, scalable, and of course interesting. So the data set that I'll be using for this project is the FUR 2013 data set with 7 emotion type classes. The data set contains roughly 35,000 examples of 48 by 48 pixel scale images of faces. Here is some laid out for your reference. So the algorithms that I will be using in this project are first a simple multi-layer perceptron, which consists of input, hidden, and output layers, and it learns via backpropagation. The second model I'll be using is convolutional neural networks, which introduces convolutional layers which extract spatial features from images, and these are typically more ideal for image data such as the FUR dataset. And third, I'll be using k-nearest neighbors, which is an instance-based model that classifies new data points based on the majority class among the k closest data points. So in this example, you can see here the data point we're trying to classify. If you use 3 of the nearest neighbors, it will be the blue class, but if you do 7, it will be classified as the red class. And we'll get more into these later in the presentation. So first, I want to just make a few references to some related problems, including data sets and models. So some data sets that are related to my project are the CK+, also known as the extended Conade data set. This contains both posed and spontaneous expressions, and it's often used for benchmarking in facial expression recognition projects. And the EffectNet dataset, which is a much larger dataset with over 1 million images labeled with both categorical and dimensional emotion labels, so it's a much more in-depth facial expression dataset. And some related models are the VGGNet, which is a simple pre-trained convolutional neural network, often used for facial expression recognition and classification, and it was developed by Oxford. And next, the ResNet pre-trained model, which uses residual connections, which create a much deeper network, and it's used for learning much more complex facial features. All right, so we'll talk about the data pre-processing now. So the first thing that I did to this data set is I removed 4 of the classes. So as I was researching this data set and looking at some other projects done with this data set, I noticed that with the 7 classes, the accuracy tended to converge to around 62%. And while this is still impressive for a 7-class data set, I wanted to see some better results and change it up a little bit from some of the other projects that have already been done with this data set. So with that being said, I removed 4 classes and relabeled each of them to an integer value just for making classification easier. So as you can see here, 3 sample images from each class and with their relabeled integer values. All right, now I'd like to go over some transformations that I applied to the data set. So as you can see here, these are the initial images, what they sort of look like. So I applied 4 main transformations to these images. So first off, that was random cropping. So this essentially just shrinks, or I guess you could say zooms in or zooms out a little bit on the images while keeping them within that 48 by 48 pixel range. And next, I applied a grayscale effect, which essentially makes training, like I mentioned, the data, instead of having a red value, green value, and blue value, there was just a gray value for each pixel ranging from 0 to 1. Next, we did a random horizontal flip and a random rotation. So as you can see, this grandma here has been flipped along the horizontal axis and randomly kind of rotate a little bit. And next, I converted each image into a tensor, which is essentially just a container for numbers arranged in a grid across 1 or more dimensions. In this case, the tensors are 3 dimensions. You can sort of think of the tensors, in this case, like a matrix with each entry being a pixel representing the grayscale value of that pixel. All right. The next thing I did in the pre-processing setup is I normalized these tensor values. So this makes the model more generalizable by maintaining similar input distributions. This is a very important step for achieving efficient convergence during training. And so as you can see beforehand, the pixels were ranging from 0 to 1, 0 being black and 1 being pure white. So I just normalized these to be from a range of -1 to 1, which is the standard in machine learning for when using images as input data. All right, let's move on to some data exploration. All right, so now we're going to look at the train and test class distributions. So one thing to note here is the classes are sort of imbalanced. The data set is not evenly distributed. The happy class is the most frequent emotion, making up roughly 40% of the train and test sets, while surprise is the least, representing around 20% of the images. And so this can possibly introduce some training bias risk, where the models may be biased towards classifying happy due to the overrepresentation during training. To combat this, we will look at a few different metrics as opposed to just accuracy alone. Metrics like sensitivity, area under the curve of the ROC curve, and confusion matrices will all be very critical when analyzing our model's classification. All right, and next we can take a look at the some pixel intensity histograms. So as you can see, the happy images show a little bit higher brightness overall, peaking around 0.6 to 0.7 intensity. And looking at the sad distribution, they're a little bit more evenly distributed with a flatter spread across the different pixel values. And then surprised class is a little bit brighter on average, peaking around 0.7 to 0.8 intensity for the pixels. So what does this mean? So the distinct intensity profile suggests that pixel brightness could be a key feature for model classification, especially when distinguishing from the happy and surprised classes. All right, let's look at the box plots analysis of the different classes. So I would like to note that these are based on samples of 100 pixels from each class. As you can see, the ranges do not indicate that each class has pixels at 0 and pixels at 1. This is not true. It's just because of the sample size. But these box plots do capture the nature of the interquartile range of each class. Notably, the happy and sad have similar mid-range intensity distributions for the pixels, while surprised shows a higher median, which is consistent with our histograms. And these trends reinforce that pixel intensity patterns can vary by emotion, even when sampled, which will be a useful for learning. All right, let's move on to model selection. So the first model that I decided to use was the multi-layer perceptron, otherwise known as the MLP. So what is an MLP? MLP is a fully connected neural network that learns patterns by adjusting weights through backpropagation, like mentioned earlier. In this case, it takes each pixel as an input feature and passes them through layers of neurons with ReLU activations and maps the pixel values to an emotion class, otherwise classifying them. I picked this MLP as a baseline model because it's simple, fast to train, and it will be easy to compare with the more complicated structure of a convolutional neural network. And it will allow us to tell if do these convolution layers really help improve accuracy when looking at images. So here's a graph of the train and validation loss for the MLP results. So the model consisted of 3 layers, each with a batch normalization, dropout, and a ReLU activation. So this model trained for 11 epochs before early stopping kicked in. Basically, this just means that the model has essentially converged. So you notice 11 epochs is pretty low. And when we look at this graph, the loss started a little bit higher, but it converged very, very quickly to 0.025, and validation accuracy reached roughly 65%. So this is not that good. We kind of want to see more convergence, a lower loss. And so basically this implies that this multi-layer perceptron is not enough to pick up on the spatial patterns of images. So hopefully the CNN will have better performance and be able to extract some features from the image data. Okay, so moving on to the CNN, what is a convolutional neural network? So convolutional neural network is essentially a type of neural network which is specialized for image or image-like data. It uses convolutional layers to detect patterns such as edges or shapes. And then activation functions such as the ReLU are used just like in a normal multi-layer perceptron. And pooling layers are introduced, which essentially help to reduce dimensionality while keeping important features intact. And then at the end, typically you'll have a small, fully connected multi-layer perceptron, at the end of the convolutional layers, which basically helps to classify based on those extracted features from the convolutional layers. So why did I choose this model? So CNNs are perfect for image tasks like emotion detection because they learn patterns directly from pixels without manual feature engineering, which is really important. And they preserve spatial structure, which does not really happen in the simple neural network. And yeah, let's move on. See the training results. So as you can see here with the loss chart, both validation and training loss converged much more than the multi-layer perceptron. So our model consisted of 4 blocks. Each had 2 2D convolutional layers, and we kept the batch normalizations and dropout the same as the MLP, and we also added a pooling layer to each block. And then at the end of these 4 blocks, we had, like I mentioned, a fully connected MLP for classification. So this trained for 61 epochs before early stopping, and validation accuracy reached about 90%, which is very good. All right, next we will move on to our final model, K-nearest neighbors. So what is K-nearest neighbors? It is a simple instance-based learning algorithm. It classifies new data points by looking at the K closest labeled points and the training set and assigns the most common class among them. So why did I choose this? So KNN is often used in classification problems. It's easy to understand, and it does not require a training process, which makes it very quick. It's useful as a baseline comparison, or you can also couple it with a CNN, which is what I did, to hopefully improve the accuracy a little bit more. And so that is exactly what happened. So essentially what I did was take the extracted features from the CNN, and instead of using an MLP to classify the images, we essentially just used a k-nearest neighbors algorithm. And so this basically just takes in a vector of the extracted features and uses those as the data points. And I tested this out with many k values, and 300 was the highest accuracy. It only slightly improved the accuracy to like 90.9, which is just a little bit better. Didn't really change much, but it's interesting to note. All right, moving on to model testing and validation. So I'm going to do a quick overview of the testing, and I would like to note that due to the computationally intensive nature of processing images and training these neural networks, I decided to only move forward with the rigorous testing for the CNN. This is partly due because of the time it takes to train the models, and also partly due because I ran out of GPU units on Google Colab and could not do this training for testing, for all the different variations of the models. So we just went forward with the highest accurate percentage, which was of course the CNN. So the plan for testing is to perform k-fold cross-validation, report accuracy, mean squared error, confusion matrix, and the ROC curve. And then at the end, I'm going to test with a few images of myself. So here are the results for the k-fold cross-validation. So all 5 folds performed very similarly, which is a good sign. It means that the results weren't just due to a lucky train test split. The average validation was around 86%, which is slightly lower than the final model's peak accuracy of roughly 90%. But this is likely just because cross-validation doesn't benefit from being trained on the full data set. So there's less images in each training fold. But overall, this gives confidence in the model's consistency and generalization. And as you can see as well, the mean squared error was consistent across all 5 folds. Next, I'll discuss the confusion matrix. So a confusion matrix is essentially a table that shows how often a model's predictions match the true labels for each class relative to the misclassifications. So from this confusion matrix, it shows strong performance across all classes. The model correctly identified happy faces around 93% of the time, sad faces around 87% of the time, and surprised faces around 90% of the time. The balance across the sensitivities suggests that the CNN generalized well without heavily favoring one class, which is good because we were worried about that class imbalance early on. Alright, so now we'll take a look at the area under the curve of the receiver operating characteristic curve. So the ROC curve essentially just plots the true positive rate versus the false positive rate at various classification thresholds. And usually a value closer to 1 means the model is better at distinguishing between the classes. So we can take a look at the curves for each class here. The happy curve was the best with a very steep curve, indicating a very high true positive rate. The sad had a little bit worse performance, as well as a surprise, but all 3 showed great results overall, reaching that 1 threshold. All right, and just for fun, I want to just quickly show a couple images that I tossed into the CNN of myself and my girlfriend to see if it would correctly classify them. So these are the original images. I wrote a function which essentially transformed them into a similar format as the training data, so black and white and 48 by 48 pixels. And the model was able to correctly classify all three images, which I thought was really cool. All right. Quickly, I'm going to go over just summary, references, and appendix. All right, so just a quick summary. So I built an emotion detection system using facial images, and I focused on scalability, interactivity, and exploring different machine learning models. So my approach was pre-processing the FIR 2013 dataset by normalizing, relabeling, and applying some transformations. And then I developed 3 different models and compared them. The key results were that the convolutional neural network achieved roughly 90.4%, which was increased to 90.9% using k-nearest neighbors. And cross-validation showed consistent performance with 86.35 plus or minus 0.92% accuracy, and personal image testing reconfirmed these results. Here are my references, and last but not least, the appendix. I just want to note here that keep in mind, if you do want to run the Colab, it will take a long time to train unless you have access to a GPU. But other than that, take a look at these notes if you want to run it, and thank you for watching.